We're going to wrap up our discussion of binary arithmetic circuits by talking about binary multiplication and division. Now, in general, binary multiplication and division is harder than what we're going to talk about today. There are more details to be considered, but this is just an introductory course, so we're just going to see the very basic way of doing multiplication and division, and that is to shift the number left or right. If you'll remember our earlier discussion about the individual bits of a binary number, you'll remember that each bit to the left was had twice as much weight as the number to the right. So 16 is twice as much as 8, 128 is twice as much as 64, 1024 is twice as much as 512. So if we took every one of these numbers, every one of the 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, and shifted every one of them one place to the left, we would have doubled the weight of each of those numbers, and therefore we would have doubled the number. And in fact, that's exactly what happens between figures 16 and 17, is that we have shifted every bit to the left by 1. We've shifted a 0 into the least significant bit, and whatever used to be in the most significant bit drops off. That goes into what we call the infinite bit bucket. And the original number was 926. And when we do the shifting, we end up with 1852, which is 2 times 926. We can also, of course, shift the number to the right. And if we shift that same number to the right, and this is kind of hard because we're shifting figure 16, we're shifting every bit one place to the right, and we end up with figure 18. And so we shifted the 0 that used to be here, shifted out, and a 0 shifted in. It was not the same 0. We'll shift a 0 in here regardless of what shifts out over here. And when we shifted it to the right, we ended up with 463, which was, in fact, half of 926. So shifting a number one bit to the left, we'll double it. Shifting one bit to the right, we'll halve it. We'll cut it by a factor of 2. We'll divide it by 2. And if you would shift it, say, 2 places to the left, then you would multiply by 2 twice. 2 to the second is 4. So you could multiply the number by 4. Or if you shifted it 3 times, you could multiply it by 8 or 16. It's very easy to multiply or divide a number by powers of 2. So I'm just showing you here in figures 16, 17, and 18, I'm showing you shifting it one place to the left or right, but you can shift it any number of places to the left or right. Now you have to be careful, because if you shift it too far to the left, notice that if I shifted this number one more place to the left, I would lose this 1. That 1 would fall off the left edge of this number, and that's not going to give you the correct answer. So you have to be very careful about overflow if you're talking about multiplying a number by a factor of 2. If you think about it, here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits. 11 bits can be used to represent any number up to 2047. If I were to double this number, I'm at 3704, which is too big for 11 bits to store. So it should be no surprise that if we try to multiply that number by 2, we are not going to get the correct result. We're going to have overflow, and that's something that would give us the wrong result. Similarly, if I were to shift this number to the right, what's going to happen is I'll still get approximately the correct result, but I will have lost a little bit of precision, because when I shift this number to the right, the actual number divided by 2, it was an odd number, so when I divide it by 2, I should end up with something 0.5. But this number can't hold a fraction, so I'm going to drop off the 0.5. It's just going to round it down to the next lowest integer. So that's something to be aware of when you shift it to the right. Similarly, one last thing is that you can shift any number of places, and you can also store intermediate results. So you can multiply by other constants that are not powers of 2. So for example, if I wanted to multiply by 10, so let's say I have a number x, I want to multiply it by 10, well, 10 is just 8x plus 2x. So if I shift left once to get 2x, store that result somewhere, shift left 2 more times to get to 8x, and then I add the 8x plus the 2x, that'll give me 10x. So if you're doing multiplication of integers, of an integer times any number, you can do it using shifting and adding. And as a matter of fact, in some cases, that's how multiplication is done. There's a very, very clever and really interesting way of multiplying 2 numbers together that involves a series of shifts and adds. And I know that you're going to learn about that next semester in ECE 221. So I'm not going to steal the thunder on that. Just know that if you wanted to multiply by any integer, you can do it just by shifting and adding, which is really interesting. So time for one more example. We've got binary multiplication and division example problem, where you'll work through a couple of these cases and verify for yourself that it does in fact multiply and divide by powers of 2.